Let's talk about ionic bonding. This is a very important topic in chemistry, so you might need to play this video more than once. It's an incredibly important topic. First thing we need to do is determine number of valence electrons. The number of valence electrons are just electrons that are furthest from the nucleus, and we can determine number of valence electrons from the periodic table. So group 1, I'll have 1 valence electron, 2 valence electrons, 3, 4, 5, 6, 7, and 8. Right? So that's just straight from the periodic table. Now every atom's goal in life is to have either 8 valence electrons or 0 valence electrons. So we're either going to gain, lose, or share electrons in order to get up to 8 or down to 0. And in today's lecture we're talking about ionic bonding, which involves losing and gaining electrons. So an ion is just a group of atoms or a single atom with a net charge. Cations have a positive charge and anions have a negative charge. So you can think about this, there's a plus sign in cation, so just think about a plus charge. Or you can think about a battery, the cathode is the positive end and the anode is the negative end. Now a monatomic ion, just think of the prefix mon, like one atom. Right? So a monatomic ion is a single atom that has a charge. Poly meaning many, polyatomic ion is a group of atoms that has a charge. So let's look at monatomic ions first because they are simpler. So, monatomic ions. Monatomic ions result from a single atom that has gained or lost electrons. Alright, so where do these numbers come from? If group 1 all has 1 valence electron, is it easier to gain 7 to get up to 8 or lose 1 to get down to 0? Well, it's easier to lose 1. And electrons are negative. If you lose a negative charge, negative ion, if you lose a negative electron, you form an ion that has a positive charge. Right? You're losing something that is negative. So these guys have all lost that 1 electron to get down to 0. So if you lose something that is negative, these all have a +1 charge. Group 2 all has 2 valence electrons, which is easier, gain 6 or lose 2. It's easier to lose 2, right? Because we want either 8 or 0. So it's easier to lose 2 to get down to 0 than it is to gain 6 and get up to 8. Electrons are negative. If you lose 2 negatives, that gives you a net +2 charge. We're going to skip the transition metals for right now because they can do some weird things. You'll take entire courses on the transition metals. Here we're at 3. It's still easier to lose 3 than gain 5. So all group 3 guys have +3 charges. Group 4 is on the line. So they're not going to go either way. We're going to ignore them for right now. Now we've got 5 valence electrons, and now it's easier to actually gain. So it's easier to gain 3 and get up to 8. So electrons are negative. So all these monatomic ions have a charge of -3. These all have a charge of -2. These all have a charge of -1. And then this group already has 8, so they're good to go. You don't need to worry about them. I know I'm going through this kind of quickly, but I don't want to make this a 20-hour video, so just make sure you're following along in your notes. When we name monatomic ions, we're going to change the suffix to "ide" if it's an anion. So for instance, chlorine becomes chloride. If it's a monatomic cation, we just put the word ion at the end. So magnesium becomes magnesium ion. And if it's a transition metal, I said we were skipping over them. Transition metals can form multiple different cations. So for instance, iron can form iron 2 and iron 3. So you just use Roman numerals. So this has a charge of +2, so we're going to call this iron 2. And this has a charge of +3, so we're going to call this iron 3. And so ionic bonding results from the attraction between a cation and an anion. It's a very, 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 very strong electrostatic attraction. So sodium has lost an electron to form sodium ion. Conveniently enough, chlorine needed to gain 1 electron, right, to get up to 8. So it gained 1 electron. And now we've got chloride, we've got sodium, positive, negative, just like magnets, click, right? So these form a very, very strong electrostatic attraction, which we call an ionic bond. Properties of ionic compounds. The most important thing that I want to emphasize here is that there's no charge in a compound. All right, when you're writing the formula for a compound, there's no charge. Think about water. Are there any pluses and minuses in the formula for water? Is it H plus 2, O minus 2? No, there are no charges. Okay? I can't emphasize this enough. When you're writing the formula for a compound, those charges go away. They've canceled each other out. So the way we name an ionic compound is we always name the cation first. We always write the cation first too, right? Start positive is the way I like to think about it. Put the positive one first, the negative one second. So for instance, NaCl is called sodium chloride because the anion ends in "ide." KBr is called potassium bromide. Cation first, anion second. So for instance, if we were naming these three, note that the subscript does not affect the name at all, right? That subscript's just telling me how many we have. So this is called aluminum chloride. This is called lithium nitride. This is called magnesium oxide. Now, if your compound contains a transition metal, you need to use Roman numerals to designate which transition metal we're dealing with. FeO is iron 2 oxide, whereas Fe2O3 is iron 3 oxide. We had to work backwards to figure out which iron we were dealing with. Oxygen's in group 6, so oxide is -2. If this is a 1-to-1 ratio, if this is -2 always, and there's only one needed to cancel it out, this must be +2. We're going to work backwards again here. Oxide is in group 6. It's always -2, right? And there are 3 of them, so this half is -6. So for this half to be +6, there are 2 irons, so 2 times 3, this must be +3, right? So that this side is +6 and this side is -6. So if we were naming these, you could pause the video and try these on your own and then check your work. Copper 2 sulfide, lead 2 bromide, and copper 1 chloride. Now note lead is element number 82. It's technically not in the transition metals, but lead is an exception. It does need Roman numerals. All right. When we're going the other way, when I give you the name and I want you to write a formula, we're going to use what's called the crisscross method. So for instance, if I say, what's the formula for sodium sulfide? You look at your periodic table. Sulfur is in group 6. Group 6 atoms all have a -2 charge. Sodium's in group 1. Group 1 atoms all have a +1 charge. So the crisscross method works like this. The superscript here, this is a +1, becomes the subscript over here, and the superscript here becomes the subscript here. Now, of course, you drop that negative because you can't have a negative subscript. That doesn't make sense. And if your subscript is 1, we ignore it. So the formula for this would be Na2S. Here's another example. If I say, what's the formula for aluminum oxide? You look at your periodic table. Aluminum is in group 3, so those are all +3. Oxide's in group 6, so those are all -2. So the superscript of 1 becomes the subscript of another. Whoops. Superscript here becomes subscript here. Superscript here becomes subscript here. All right. Those are all formulas involving monatomic ions. Polyatomic ion is a group of atoms with a net charge, and you're just going to have to memorize your polyatomic ions. On page 168, you're only responsible for 7 polyatomic ions. So in your textbook, page 168, ammonium, acetate, carbonate, hydroxide, nitrate, phosphate, and sulfate. Those are the only ones I'm going to make you memorize in Chem 1120. If you're watching this as a Chem 1132 student, in general chemistry, you got to know them all. But in intro chemistry, you only need to know 7. All right, now the rules for naming with polyatomic ions are just the same as the rules for naming with monatomic ions. You're still going to put the cation first, but now you just need to recognize when you've got a polyatomic ion. All right, SO4 is sulfate. So this is sodium sulfate. PO4 is phosphate. So this is potassium phosphate. And the crisscross method still works when you name compounds involving polyatomic ions. So if I said, what's the formula for calcium phosphate? Calcium is +2, phosphate is -3. So superscript here becomes subscript here, superscript here becomes subscript here. Now you need to put that polyatomic ion in parentheses to tell the reader that you've got 2 phosphates for every 3 calciums. If there's only 1 of that polyatomic ion, then you don't need those parentheses. But here, because that subscript is 2, you need parentheses around phosphate. Here's another example, lithium carbonate. All right, we're not going to need any parentheses this time. Lithium's in group 1, so that's +1. Carbonate has a -2 charge, so superscript here becomes subscript here. This is +1, superscript here becomes subscript here. There's just 1 carbonate, so you don't need those parentheses this time. Here's an example involving ammonium, which is the only polyatomic cation you're responsible for in Chem 1120. So this time we're going to put the parentheses around the cation. Right? This is ammonium, it's NH4+, so the subscript here is 1. Superscript 2 becomes subscript 2 here, so now the parentheses go around the cation. Alright, I cannot emphasize this enough. The only way to get good at formula writing is by practice, 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 practice. So download the practice problems from Desire to Learn. Do the problems that I suggest in the syllabus. Work out the problems in your textbooks and in the homework, because practicing is the only way you're going to get good at this. The end.